Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's start. So it's great to have Nikhil Devanur today speaking about fast algorithms for online stochastic convex programming. So Nikhil is an expert on approximation algorithms, online algorithms, and algorithmic game theory. Yeah, and today he's talking about, I guess, online algorithm, right?
Thanks, Kostya. Thanks. It's nice to speak here. I think speaking after a long time. So it's nice to be in a podium. And I will talk about this work, which is joint work with Shipra Agrawal from MSR India. So as many of you know, I spent about a year in India, and this is one of the 2 papers I wrote when I was there. Really like both of them. And it's a very simple talk. I'll define the problem, I'll give you the solution, I'll point to some future work. So what is the motivation? As again many of you know, I've been working on problems coming up in display advertising. Now these are the things where we advertise on people's t-shirts. Just kidding. And previous to this work already, the algorithms we designed are actually being used by Microsoft in the past few years to run this display advertising. And here's the basic problem formulation. The basic decision you have to take in this problem is you get an ad slot or an ad opportunity, and this is called an impression, so this is a technical term, and you have to assign this impression to one of many competing ads. So which ad do you assign the impression to? So if you assign an ad j to impression t, then you get some value vtj that depends on this pair. Now you could say, okay, why don't you just assign each ad to the each impression to the advertisement with the highest value? You don't do that because there are constraints. The constraints are each ad has a target number of impressions, and you don't want to assign more than these many impressions to this advertisement. Okay, it's still an easy problem if you know everything. Here's an LP relaxation, you can solve this LP relaxation, you can also round it very easily, right? So you want to maximize the total value generated by the allocation. This is a capacity constraint. For every ad, j is an ad, you cannot assign more than gj impressions, and every impression you can assign to one ad. Okay. The difficulty comes from the online part. Thing is, you don't know this entire thing ahead of time. The impressions come one at a time, and you have to assign the impression without knowing what impressions you're going to get in the future. So this uncertainty about the future is what makes the problem difficult.
So your XTJ less than 1, meaning that it's just one.
It's just one impression.
One impression.
Just assign it to one of the ads.
One impression can only take one ad.
I'm sorry?
One impression can only take one ad.
Yeah. So it's just impression by impression.
There is a sum of a t.
It should be j.
Oh, this is j. Oh, sorry, yeah.
Yeah, that's what.
That's what happens when you copy paste. Yeah. There should be some more j. Yeah, I changed this thing here. Didn't change this thing here. Okay, so we in this paper, joint with Balu and others, we designed a near optimal algorithm in a particular stochastic model. I'll mention what the stochastic model is later. And this is algorithm with some modifications that is being used by Microsoft. And then we met this guy called Reality. So I'm exaggerating a little bit. The thing is, this was an essentially linear formulation, and in reality there are all these non-linear things that creep up. So one thing is called the under delivery. So the way this works is, this target is not just an upper bound, it's essentially upper and lower bound. So this is the number of impressions you promise the advertiser, and if you don't give these many impressions, then you pay a penalty. So if you promised 1,000,000 impressions, you only gave 90%, you have to pay a penalty for this 10%. And if you assume that this penalty is linear, then it still becomes a linear program, it's a linear formulation. But in reality, this penalty is non-linear, it's some kind of convex. So if you give 50%, then it's, it's really bad. So it's a non-linear penalty. The other thing is, arbitraries, they require a mixture of different impression types, and it's, if you deviate away from this mixture, then it's not so good. But okay, so how does it look like? So again, it's not a linear relationship, it's some kind of a convex penalty. So the farther there is an ideal mixture, let's say you want 50-50 of men and women, but the farther you deviate from this ideal, the worse it is, and again it's not linear.
Do you always really know whether it's a woman?
Yes, we know a lot of times. Most of the time we know, because they're logged in, they've told us what their gender is. So that's just an example, we might know other things.
So, Nikhil, you're saying it's not linear, but it's well defined. I mean, someone tells you exactly how bad it is to have 48% men and 52% women. There is a score that defined by some human?
Yeah, so you can model it, it's a little fuzzy. So advertisers don't really give you this function, but you can kind of capture this. So advertisers don't tell you here's a penalty, but so someone who knows a business can model this and say, okay, look, if you deviate too much, then this is how bad it should be. So some human will come up with this function.
So, but at least for under delivery, it's precisely known.
Under delivery, yeah, this is part of the contract. So this is part of the contract, so you know exactly.
But for you, the algorithm designer, I don't care what.
For the algorithm designer, this function is given. This function is given.
Okay.
This function is given. Okay, and another place where this comes up is this value that I said. So there are many things we care about: revenue, of course, also relevance, and maybe clicks, conversions. There are all kinds of things we care about. One thing you can do is just take a linear combination. So then it becomes this linear objective again. But that may not again capture what you really want. So you might, again, what you really want to optimize might depend in some nonlinear way on all these different objectives. Okay, so there are all these things that are not captured. But the nice thing is either they occur as a concave objective or a convex constraint. And this is like a convex programming version. Right? So from linear program we can go to convex program. In the offline world we still know we can solve this, so there is hope. So in practice what we do is we took the linear programming algorithm for linear programming, and you do some hacks, you do some changes that kind of make sense, and it still works pretty well. But as a theoretician it was not a principled approach. So I really wanted to figure out, okay, how can we handle these convex things that come up. So that's what drove this problem. Okay, so now I'm going to give you a very general problem formulation that is going to capture all these things, and we call it online convex programming. So we thought of online convex optimization, but that was already taken, so we had to settle for online convex programming, but I think it's a very apt thing. So here you are given a convex function f and a constraint set s and a time horizon t. This you are given ahead of time, and this is not changing. So this is what you are talking about. The algorithm is given this objective function f. Okay, this is the input. Now this definition, it's going to look very abstract. So bear with me for a moment, and I will show you how this corresponds to the kind of problems we are talking about. So abstractly, in every time t, a request arrives, and what is a request? It's abstractly just a set of options, and what the algorithm is required to do is pick an option from this set. What is an option? Each option is associated with a certain vector, okay, and this vector can correspond to cost or reward. So some dimensions can correspond to cost, some dimensions can correspond to reward, and so on. So you encode everything in this vector. Okay, so the choice set is just a set of vectors in R to the d, and the algorithm has to pick one vector from this set, has to pick one option from this choice set in every time, and then again this is an online problem, so in every time you don't know what the future is going to be, you have to do it in an online fashion. And what is your goal? The goal is to maximize this function f that is given of the average of all the vectors that you pick. So you can think of it as a function of the sum, but it's just more convenient to think of it as an average for us. But the two are equivalent. If you know the time horizon, you can just scale everything. Okay, so this is, and then the constraint is that the average has to lie in S. So this is a global constraint and a global objective because it binds across the decisions you take across time. So it's not per time step, it's across what you do through the entire time horizon, right? So the average of everything has to lie in S.
So the constraint corresponds to some capacity constraint.
Yeah.
Then does it make sense to average it over time? I mean, I don't want to violate any capacity throughout time.
So yes, that's a very good question, and that was a linear formulation, linear programming formulation was you had this capacity constraints, and when you specialize it to that, we can actually make sure that you always satisfy it. But if you have arbitrary constraints, then it's not possible. In the intermediate steps, it may not be possible to satisfy everything. So it may be possible to only satisfy everything in the end. So for this generality, you need that everything is only required to hold at the end.
So in particular, you know the time horizon.
Right? You know the time horizon.
Because otherwise I could end any time and expect you to be in S all the time. Right?
Yeah, you know the time horizon. Like think of the opposite of packing, the covering. In that case, you can only hope to satisfy it at the end, for instance. So let's go back to the, yeah.
Just to make sure I understand. So the thing you don't know is AT.
AT, you don't know what ATs are.
And if you knew all the ATs ahead of time, then it would be just a standard convex
It's like a
program.
convex programming, yeah.
Why? You don't know the VT? Oh, I see.
So, okay, assume each AT is convex, if you want. Then it becomes convex programming. Otherwise, it's not. If ATs are discrete, there is still a notion of this issue of discrete versus continuous. But because we're averaging, that is only like a 1 over t thing. Another thing that I should say is this is not really. We assume this is bounded, so this is not really r to the d. It's -1 1 to the d. So then this discreteness issue is not a big issue. So it's essentially convex program. Okay. So think of AT as just a polytope.
You're saying you might as well take the convex hollow of these
Convex hollow of these things, yeah. So we're going to ignore rounding issues because it's going to be easy rounding. All right. So what about the Dirichlet problem? So this is a generalization of the Dirichlet problem. How is it a generalization? Here's how I can encode it. The vector has n plus 1 dimensions. So if there are n advertisers, it has n plus 1 dimensions. The first n dimensions encode which advertiser this corresponds to, right? So there's a 1 in the dimension corresponding to the advertiser, and the last dimension corresponds to the value. Okay, and your objective is just the last dimension because you just care about maximizing the total value. And what's the constraint set? The constraint set is this capacity constraints, or box constraints, right? I just divided by t because I'm the constraint is on the average. Okay, so for in the jth dimension, you cannot exceed more than gj by t. Okay, so if you pick this vector, it corresponds to assigning this impression to this advertiser that uses up one capacity and it gives you a value of VTG. Right, so it's clear how this encodes the Dirichlet problem, right? And now let's say you had an under-delivery penalty, a non-linear under-delivery penalty. Here's how you would change it. Instead of defining fx to be just the last coordinate, you would have this penalty here. So gj encodes how this penalty looks like. So gj only depends on xj, which is the count of the number of impressions you assign to advertiser j. Okay, so you would have something like this. And if g is convex, this is concave, so you can maximize this. This also generalizes a more general linear version called the online packing. You have these packing constraints, and you can do a similar thing. One example of an online packing is a network routing problem, where the ith request corresponds to a request to route one flow from a node Si to node Ti in a network. You have edge capacities are given ahead of time. So that's a packing problem. Another example is a combinatorial auction. So buyers arrive, they have combinatorial valuations for sets of items, and let's say you have many copies of each item. So buyer arrives, he has some valuation, you have to maybe offer prices or do something else. You ask him to tell you your valuation in some way, and then you assign a bundle of items to him and you charge him something, and then the next buyer arrives. So this is also an online packing problem. So these kind of things can be encoded in this format. And even though I said for the online packing this is a linear version, this is already solved, even for this we get an improvement. Improvement is technical. So earlier the dependence, this guarantee that we get, that I'm going to show later, it depended on the number of constraints. And the number of constraints in this formulation, for instance, like a network routing formulation, the number of constraints could be exponentially the number of variables, right? Because if graph has m edges, the number of paths could be exponentially in n. So the number of constraints would be exponential, and we get a dependence that's only depending on only on the number of variables. So even in some cases we get improvement, even in the linear cases. And there are potentially other applications. We are looking into this, and people are studying similar problems. Some of it fit exactly in our model, some of it needs some work, and some of it it's not clear the fit. Hopefully we can extend these techniques to that. So there's a lot of work in especially operations research community that look at similar problems. Okay, so one thing that I haven't told you yet but mentioned is this thing is in a stochastic model. So what is this stochastic model? So this is not the usual worst case model of competitive analysis. So the model we consider is called the random permutation model. So this should be familiar to people who have seen the secretary problem. In this model, this collection of the sets ATs is adversarial. So an adversary picks the collection of ATs, but the order in which these are presented to the algorithm is random. So it's a uniformly random order. Okay, and that's the random permutation model. And that's the stochasticity is only in the order in which it comes. There is a related model called the i.i.d. model. In this case, there is a distribution on sets of vectors. So it's not a distribution on vectors, it's a distribution on sets of vectors. And every time this AT is generated from this distribution, it's an i.i.d. sample. And now the difference between these two is like the difference between sampling with and without replacement, right? So intuitively. And it's known that this is the more difficult model, so any algorithm that works for this also works for this, but not necessarily vice versa. And there is also a model with time varying distributions. This is like the generalization of i.i.d. that is not covered by random permutation. So random permutation is inherently stationary. We can allow the distributions to change over time, but I will not go into the detail of this. So for this talk, I am just going to talk about the random permutation model. So just think of this.
So chosen adversarially, but not unknown to me.
Unknown to you. All you know is that they are coming in a random order. Okay, and how do we measure the performance of the algorithm? We look at an additive notion which is called the competitive difference. So this is basically the difference between opt, which is if I knew everything, what would I do? I would pick some vectors to be so that the average is in the set and maximize this function of the average. So that is opt, so offline optimal solution, and we look at the difference between that and what we get. The thing is, we cannot make sure that our average is actually in the set S, but we'll make sure that the distance from the set is small. So we have to, it's like a bi-criteria, we have to relax the constraints a little bit. So both of these will go to 0, as you will see soon. And in the special case, so the traditional thing is this competitive ratio, which is a multiplicative thing, and this is what is used in the linear version, for instance. And the difference there is, again, as Ishai said, the constraints have to be satisfied at all times in this packing problem. This is too strong for the general framework that I said, but when you specialize it to this, we can make sure you satisfy the constraint at all times, and you can also make sure that we get a competitive ratio. So it's not like we are kind of playing some games with this, it's just the nature of the problem. It's because of this generality we have to do additive. So if you specialize it to this, our technique also gives you multiplicative errors.
There's something, is there some constraint on f except that it's convex or
it's Lipschitz.
It's Lipschitz.
Okay, so what has been done previously? I said mostly people have worked at the linear version and this online packing especially, and there are a bunch of results that that are dual based. So essentially the idea is to learn an optimal dual variable to this packing problem and use these dual variables to do the assignment. This is efficient in the sense that it has to solve a batch LP, maybe logarithm in the number of time steps. So log t times it has to solve a batch LP, but every step picking this vector from this choice set is fast. So in that sense it's efficient, but it is suboptimal. So the guarantees that you get are not optimal. And then there was this paper that I mentioned earlier that is used. So this uses something called a hybrid argument. It is both efficient, it also solves a batch LP log times, and it gets an optimal bound for the i.i.d. model, but for random permutation model it's suboptimal. So we didn't know any bound for random permutation. So it only works for the i.i.d. model. And then last year there was this paper by Kesselheim et al. That used a primal approach, so there are no duals here, and it was optimal for both the random permutation and i.i.d. model, but this was really inefficient. It had to solve an LP in every time step. So every time step to pick this vector, it has to solve an LP, and okay, this is polynomial time, but this is not something we would ever use in the advertising application or most of the applications for that matter. And so this result gives the best of both worlds and also generalizes to the convex program. So it is efficient, and so it's a primal-dual approach. We have to solve a batch LP or a batch convex program. In the convex programming case, we have to again solve it the log times, but for LPs we have to solve it only once. So it improves even on these things that have to solve log times, and it is optimal for both RP and random permutation and i.i.d. models. And also another thing that I like a lot about this is these earlier ones, all of them, the proof is quite complicated. It's not clear it's not completely clear what's happening, and here we give a very simple and modular proofs. So we have different components, and it's easy to see how these components interact with each other. And simultaneous or related to our work, people did similar things, but this is only again for the linear version. So they give similar results for the linear version that match ours, and this is also again a linear version, but they have some local convex concave objectives, not like the global concave objectives that we have. Okay, so what do we get? Essentially we get close to optimal results. We get this comparative difference of 1 by square root t, so this goes to 0 as t goes to infinity. This should look familiar to the people in online learning, this square root t regret. In particular for the objective, we get this 1 over square root t times z plus L. L is the Lipschitz constant of the function that you asked about, and z is another parameter of the problem. It's a problem dependent parameter that I will talk about later. And for the constraint, there is no such thing, it's just 1 over root t. Okay.
But assuming everything, all the vectors are in the
Minus 1,
hypercube,
1. Minus 1, 1, yeah.
What is C?
C is just some universal constant.
Oh, okay. 'Cause you
Yeah,
have-
I don't know why I have order and C, yeah. And the thing is, we get even better for some special cases. So if the function is smooth, if the objective function is smooth, you can actually get log regret. And this was not known earlier. And this is tight in general, even for linear problems. But if the function is smooth, you get log regret, and this comes from the corresponding log regret for strongly convex functions for online learning. So you get the corresponding things here, and you will see why we get this, because of this kind of a modular proof. So we use this online learning as a black box, and any improvement in the regret there translates into improvement here. Yeah, this is Hassan.
So smooth, I mean.
So smooth here translates to strongly convex in the online learning.
Why? How?
Because that's the Fenchel conjugate of this. So online learning will have the Fenchel conjugate of f. So smooth becomes strongly convex there, and then you can use
Should I be able to see that immediately?
that the Fenchel conjugate of smooth is strongly convex.
That is fine, but.
But why you get the dual?
Yes.
No,
Okay.
I haven't told you, so you shouldn't. Yeah, I mean maybe you can, but I couldn't. Okay, so yeah, and as I said, in the special case of online packing, we get the optimal commutator ratio that was known before. Okay, so now to the good part, the algorithm, right? What I'm going to do is I'm going to consider a very simple special case. It's a one-dimensional problem, okay, and there are no constraints. There's only an objective. Okay, so all you're given is, for the sake of the diagrams to be nice, I'm going to switch to minimizing a convex function. Okay, it's equivalent. So you're given a convex function ahead of time, and that's all you're given, and the number of time steps. And in every period, you see a set of points. So again, this should be minus 1, 1. So you see a set of just real numbers. You have to pick one number. So you see some numbers on x-axis, you pick one, and then you repeat. And the goal is to minimize the value of this convex function on the average of all the numbers that you picked. Okay, so this is a game. And we measure this comparative difference, we compare it to the optimal choice on hindsight. Okay, so here's an example. You're given this ahead of time, and in the first time step you get 2 points, you have to pick one, and then next step you get, let's say, 2 more points, you have to pick one, and you repeat. Okay, in every time step you get 2 choices, you have to pick one. Okay, and these are the points you picked. We're at the end of the algorithm, and we compute the average of these points, and we look at what the function is at this average. This is what we got, and you can look at all the points, all the choices you had on hindsight after everything is done, and you can say, okay, if I knew everything, I should have done something else, and that is your optimum solution. And if you had picked these, you would have got this as the average, and you would have got something here. And okay, this should be comparative difference. So earlier we used to call it regret, and somebody pointed out this is called comparative difference, not regret. So yeah.
Computing the best thing in hindsight, how would you do that?
It doesn't matter, just you use exponential time and do it.
It's not something that could be done.
So you can approximate it very well, once again. You could solve like a convex program and you could round it, and it's going to be very close. So, but for this sake, you might as well take exponential time and compute the optimal thing. Doesn't matter. You're going to see how we're not really going to care about. The analysis is somehow going to get away from having to characterize this exactly. So you'll see how it doesn't matter.
So did you have that set as here or the convex set?
So here there's no constraint. There's only an objective. So this is like a very special case, but I just picked this to illustrate the algorithm, the main ideas. And everything that I said generalizes very nicely. Okay.
So this choice of the average and the regret will depend on your random samples. Like if you did the same random sampling.
So in the random permutation model, the optimum solution doesn't depend on the stochasticity because the order doesn't matter. In the i.i.d. model, it would matter, then you take the expectation of the optimum. Okay, so here's the algorithm. In every time step, the algorithm is going to pick a tangent to this convex function. So this is a tangent. I'm going to parameterize the tangent by the slope. So the slope of this tangent is theta 1. And if you fix theta 1, you think of this as a linear function of x. And I'm going to pretend that this is the function that I'm really optimizing. I'm going to forget about h. I'm going to just try to optimize L. Okay, and in one dimension, it just means that if the slope is negative, you pick the point on the left. If the slope is positive, or whatever, the vice versa. If slope is positive, you pick the point on the left because I'm minimizing. If it's negative, you pick the point on the right. But you can imagine in many dimensions, this is going to be non-trivial, right? So, in many dimensions, I'm going to have a hyperplane, I'm going to have a linear function, and given all the points, the choice set AT, I'm going to optimize this linear function over the choice set AT.
So here you will always choose either the leftmost or the rightmost point?
Yes.
Should it be clear to me that even
it's a linear function, right?
No, I understand, but in the offline, if you take the offline problem.
Not offline, this is the algorithm.
No, I understand, but if now go to the hindsight, you have the offline problem.
Yeah.
You have one problem is the original problem, just choose the optimal allocation. The second one is choose the optimal location, but you're restricted only to
the offline,
the left or the right one.
Yeah.
Isn't there even there a gap?
There shouldn't be because of this.
Should it be clear to us why that's the
It shouldn't be clear. It's not clear a priori. That's a very good point. It's only because this works, there shouldn't be a gap. Because here in this case, algorithm is only picking one of the endpoints. Well, it's a convex function, so yeah, that's a very good point. It's not clear a priori that you can restrict the algorithm to do one of the two and get something close.
Without the online part.
Yeah.
It's even not true. If AT is always, 0 and x star. Always, all the time. 0 x star, 0 x star. I mean, maybe your algorithm will do something. Yes, yeah. Your algorithm will do something smart.
You'll just choose x star. What do you mean?
No.
At the beginning, it could choose 0.
I mean, but think of just answer the offline question. You know everything. So,
yeah.
But I'm restricting
but
you
then
to
if you start to do 3 points.
You have to have 3 points or more than 2 points for this. I mean, if there are only 2 points, of course, you're either picking the leftmost or rightmost. So you have to have 3 points or more for this to be non-trivial. So you can imagine actually that if you have many points, and maybe the points in the middle, you always want to keep picking the points in the middle. Whereas the algorithm will keep picking the extreme points, and it's not at all clear why this could do as well as the point in the middle. I mean, that's a very good point. It's not at all clear. It's only through the algorithm that it has to be.
And the gradient you're looking at, that's at the current average?
No, I have somehow picked theta 1.
That's still.
And I'm looking at the tangent to h with slope theta 1. And think of this as a linear function of x.
Sure.
And I'm going to pick the point that minimizes this linear function.
And x is your current x?
No, so now I'm going to think of this as a linear function of x. I have two choices. Which one minimizes?
Whatever theta. Theta is the slope of your current position.
It's the slope of my current linear function that I'm going to pick.
Yeah, but I guess the question, is on the next slide. How do you pick it?
Yeah. Okay. Yeah. So yeah, first time I pick somehow. Okay. So I just pick the one that minimizes. Now, how do I pick it in the next time step? I'm going to use this online learning as a black box. I'm going to feed what happened, essentially this xt, to that, and that is going to spit out the next slope. Okay, and I'm going to use that slope now. So it spit this slope, and now when I get these 2 points, I'm going to pick this one, Okay?
Sorry, so
And I repeat.
what happened?
So, okay, I picked theta 1 somehow.
Yeah, that's right.
Arbitrary, it doesn't matter. And that told me to pick this point. Okay, now I'm going to feed this to this online learning black box. Exactly how this thing is going to work, I'll tell later, but some black box, I'm going to feed it, and that black box is going to tell me what to do, what slope to pick next. So it's going to say, okay, pick this slope. Now I'm going to next pick the tangent with this slope, right? And I'm going to repeat. So now I get these 2 points, and this thing says I should pick this one. So I pick this point, and then I'm going to repeat it, and then I again go back to the black box. That's going to tell me what the next slope should be. So now you see where the feasibility comes in.
There's something more, right? When you keep saying it's a tangent.
Yeah.
That's a very specific linear function.
So actually the y-intercept doesn't matter.
Okay. It doesn't matter.
It doesn't matter for the choice, but it matters for the analysis.
Okay, matter for the analysis.
Yeah. For the choice, it doesn't matter, right? If you move the tangent function up and down, the y-intercept is where the Fenchel conjugate comes. So that's the Fenchel conjugate of
So
theta.
you basically look at like where a line with the slope touches the.
Yeah, usually there's an explicit formula. So this is always going to be the Fenchel conjugate of f star of theta. So it's just f star of theta plus x times theta.
Well, the black box takes is just the slope. But the online learning.
Yeah. So yeah, it takes this xt is all that matters really.
Oh, it takes x. Oh.
Okay. Assuming it knows h. It knows h. It takes. I'll tell you exactly what the black box does later. But think of it as a black box, and it uses. There's a black box, and there's inside another black box of online learning. So think of it like that.
You define some kind of reward.
Yeah, I use this to define some kind of reward in that time step, and that's going to tell me the next one.
So the input to that black box include not only the previous slopes, also the previous xt where you touch this.
Yeah, I'm going to tell you exactly what that is. So for now, wait, have some patience for that. I'll tell you what it is. It's coming soon. Okay, the algorithm is clear, right? There's some black box that keeps updating the theta, and that uses online learning. What I've not told you is how to define the reward. Okay, so that's the algorithm. So every time I just do this, repeat it, that's how I pick the points. Okay, so we're done. This is the average, and this was the optimal on hindsight, and this was the computative difference. So now, what's happening? So here, I want to look at the average of the linear functions that I used. Okay, so I use this L of x comma theta t. This is what I pretended I was optimizing, and I want to look at what happened, in this case. And what I'm going to argue is this is a lower bound on this h of x star. Okay, and then now this is an upper bound on the computative difference. So I only have to bound this gap. I really don't care about what x star is. Okay, this is assuming that this is a lower bound. It's not clear why this should be a lower bound. Okay, so what is this gap? This gap is the actual function h at my average. So this is the actual function that I should have been minimizing, and this is my pretense function that I was pretending that I was minimizing. So what's this difference between the actual function and my pretense? Right, this is the gap that I have to bound, and this gives me a bound on the computative difference.
It is a lower bound because you use the tangents.
No, the lower bound uses stochasticity. It's not true always, because I want it to be x star. You'll see a little bit. I'll show you why this is a lower bound. It is a tangent, yes, but there is more to it, because this is only true. So now think of, I said, think of random permutation, but for a moment this holds actually only for the i.i.d. case. Okay, so think of your drawing, think of the empirical distribution, right? You've seen everything, and now let's say you draw one of them at random. So think of your sampling from the empirical distribution. And let's consider the expectation of this draw, expectation of this L of xt comma theta t. Okay. For each pair, the one that we picked minimized L, and so it is smaller than the one that would have been picked in opt. So x star is an average of the optimum choice. So here's, because we are optimizing for L, we picked the best one, so it is better than the one in the opt, and that is why this expectation of this is less than L of x star of theta t.
But so xt is your choice at t.
So what is this expectation over?
Is xt your choice at
xt is my choice at theta t.
It seems like it's true without the expectation.
So actually, okay, so
Why is this not true without the expectation? You're just saying xt is optimal for theta t, so it's better than x star.
So actually here what it should be is
not necessarily
x star is an average.
Oh, it's not in your set. Gotcha.
Yeah.
I see.
So if you fix theta t, and now you're picking these pairs at random, and you're picking the optimal one. So for every pair, what you would pick, like point wise, you're better.
Yeah.
So here in this, when you take the expectation, you just get x star.
So this expectation over which randomness is it?
So this is, you fix theta t, and you pick expectations over, you pick the AT at random. Which set you are optimizing. So this holds for the i.i.d. model, because there every time it's a random sample, and this is exactly the difference between random permutation and i.i.d. So for random permutation, the expectation is going to be slightly off, and what we need to do is we have to look at what the difference between the expectation for random permutation and i.i.d. is cumulative over all the time steps, and that's exactly, we get an extra error term because of that, and that is also like 1 over root t, so everything works out. So this is exactly the point where random permutation and i.i.d. differ. So this was one of the things where we didn't understand, okay, why do they differ? The earlier analysis didn't throw any light, but whereas here we capture exactly where the two differ.
The difference corresponding to this 1 over root t also becomes log t over t for the smooth version.
Yeah. No, actually for the smooth version only works for i.i.d. Because this root t, yeah,
it's
you get this root
there,
t,
right?
yeah, so
okay.
that only works for i.i.d.
Okay, yeah.
And is it the only place where you will use a stochastic model?
Yeah.
So you could also say that the AT could be completely adversarial, but you just want x star to be in the convex hull of the AT at every time step. And if that's true, then
Yeah.
which can be recurrent.
Yeah. This is the only step where we use the stochasticity. And yeah, this is because we are using a tangent. But this step is like the non-trivial step where we use this stochasticity. Okay, so that's why in expectation this is a lower bound. It's not true point-wise, some points it may not be, but in expectation it's true. And we can also convert it into high probability, so that's fine. Okay, so the summary of all this is we can forget about x star, we just have to bound this gap now. The gap between the h at the average and the average of these linear functions. Okay, and this is where, okay, so I already gave some of the proof. So this is where online learning comes into picture. Okay, and what is online learning? I think most people here know, but let me do a quick summary. You want to make accurate predictions using what's happening, what happened in the past. So at any time t, you want to predict some vector theta t in some domain, and after you predict this, you get a reward, some reward LT. Think of this as a concave function, and you want to maximize. So here again, these are reward vectors. You want to maximize them, and the regret is, if you knew all the reward vectors, then what would be the single theta that you pick on hindsight versus the thetas that you picked the reward of the thetas you picked online. Okay, so this is a problem. This is an online learning problem. So notice here that these are local, unlike in our case where things were global. So this is only sum of t LT, right? And there are many algorithms available here that essentially get this 1 over square root t regret. So here I defined everything in terms of average, so that's why it becomes 1 over square root t. Okay, so how do we use this? In fact, it turns out the way I've set it up, the gap we had to bound is exactly the online regret. If you define the this else correspondingly, accordingly. Okay, so the reward that we use is this tangent. Okay, so now think of this as a function of theta. Earlier we were fixing theta and we were thinking of it as a function of x, but now I'm going to fix xt and think of it as a function of theta. So this is a convex function and this is a reward as a function of theta that I'm going to feed back into the online learning. Okay, so what is this function? If I fixed xt and as you change theta, the tangent changes and it's the value of the tangent at xt. Okay, so this is a concave function because here we are maximizing.
Sorry, I'm a bit confused now. I've got a set AT, right? What is
xt is what I picked. I picked some point xt. Now I have to go to the online learning and define what the reward function is for this time step.
Yes.
For it to spit out the next one, right? And what is that reward function? It's a function of theta, right? Now fix xt and look at this L of xt comma theta. That is a function of theta.
It's a tiny bit confusing because xt could change. I mean, there are two xt's, right? We have the slope, and at some point, if I tilt it that way, then it's another xt, right?
No. xt is whatever I picked in the vector that I picked in the last time step.
So this is to pick theta t plus 1.
It's xt dagger.
Oh,
I think
okay.
So my algorithm picked a particular xt in time step t.
So here you're picking theta t plus 1.
Here I'm picking theta t plus 1.
That's good. That's what we're getting.
Yeah.
Okay, the algorithm picked a particular xt. Now I'm going to use this xt to define the reward for the online learning. Okay, so people had questions about what this reward is, what it uses. So this is what it uses. So if you fix xt, that defines a function of theta, which is you look at the tangent with slope theta and look at how much this tangent is at this xt, and that is the reward. And this is a concave function you can show. Okay. So now what is this online learning regret? So it is a reward of this optimum choice on hindsight minus whatever the algorithm played. So this is exactly the second term, in our gap, this is exactly the lower term, right, that we had. And I'm going to show in a moment that this term, the optimum on hindsight, is going to be exactly this h of the average. Okay, so this regret is exactly the gap that we wanted to bound. Why is this? So note that L is linear in x. Okay, so for any theta, so theta star, look at the optimum one, right, or any theta star, any theta, this average, I can just take the average inside because L is linear in x. It's a linear function, right, if you fix theta. Okay, so now what is this function? This is, you look at the average, and for any theta, you look at the tangent with slope theta and what the tangent is at this average. Now you want to pick the theta to maximize it. So what would you pick? You would of course pick the tangent at the average itself, right? Because if you pick anything else, you would only get a smaller value. So obviously the best thing to do is to pick the tangent at the average, and then you just get the value of the function.
You pick the tangent at the average, but tangent still is if it is non-zero slope, then it can still.
What is this function? This function is you pick any tangent look at what the value of the tangent is at the average. That is this function.
Okay, for convex function, that has to be at that point. Yeah.
I mean, this is my definition of L, right?
Yeah. No,
L of xt comma theta, and the function of theta is, if you take the tangent with slope theta, what is this tangent? What is the value of this function at xt?
For convex H, that's only.
For convex H, of course. Right. So this best thing on hindsight is exactly H of the average. So this regret is exactly the gap we wanted to bound. Okay. So that's it. So note that there is a switch here in some sense. This thing, the best thing on hindsight is somehow the performance of the algorithm, right? How much the algorithm got, and this online learning thing is somehow the lower bound on opt. So there is a switch, which is interesting, but maybe it's natural. I don't know. Okay, so here's the overall algorithmic approach. The same thing extends to many dimensions. Now consider the case where, like in the special case, you either have only an objective or only a constraint. So if you have only a constraint, it's like having only an objective, which is just the distance of the set. Okay, so if you have only the objective, then in many dimensions you do exactly this. And so these thetas are like Fenchel conjugates. So these thetas give you some kind of linear function. You can interpret it as shadow price and so on based on the specific scenario. And all you're doing is you're optimizing this linear function given by theta over this choice set. Okay, and then you're getting this, and you're feeding this to the online learning. You're defining the reward appropriately. It's the same thing. You take the tangent in this dimension, and then it's a linear function. Or sorry, it's now still a concave function of the thetas, and that's going to tell you what the next next slope should be, and then you repeat this. Right, so exact same thing that I said works in any dimensions.
The only LP you solve is for finding theta 1.
So, okay, in this case, when you have either only an objective or only a constraint, I don't have to solve any LPs. I have to solve LPs when I have both. Even in the earlier work, we don't have to solve any LP if there is only an objective or only constraint, right? Okay, so now what happens when you have both objective and constraint? So we're going to run two separate instances of this, what I showed in the previous slide. Okay, so for the objective I'm going to have this thetas, for the constraint I'm going to have the lambdas. But now how do I pick the vector? I'm going to combine these two. And I'm going to combine this using a value z. Okay, so what is this z? It's a trade-off between the objective and the constraint. It says if I violate the constraint by epsilon, how much does the objective change? So opt of epsilon is I take an epsilon ball around S. So I take all points within epsilon distance around S and look at the opt of this relaxed problem. Okay, that's opt of epsilon. Opt of 0 is just opt. And z is this derivative of opt of epsilon with respect to epsilon. So this is what I said, if I violate the constraint a little bit, how much should I expect to get in the objective? And you either assume that you're given this z ahead of time, or you can estimate from a sample. So this is where we need to solve like a batch LP or a batch convex program. And the thing is, we only need a constant factor approximation to this. So we don't need very accurate estimate. So we need a constant factor approximation to z. So it's a much easier estimation problem. Okay, and then what we're going to do is in every time step, we're going to combine these two. So we have the theta and then we have the lambda. We're going to combine them using the z. So this is again a linear function, and then we're going to optimize this linear function over the set. Okay.
So this is also the reason why you do not solve LPs often, right?
Exactly.
Because even with a small sample, you get a constant factor anyway.
So
the initial small sample.
Very good point. So for the LP version, we only have to solve it once to get a constant factor.
Small sample suffices.
Yeah, a small sample is enough, and only once is enough to get a constant factor. So like I just need epsilon squared order epsilon squared fraction of all the requests. So if there are t requests, I take epsilon squared t samples, and that already gives me a constant factor approximation. Okay, so I only have to do it once. So why does this work? Now, okay, so the analysis is a little more complicated, and I don't have the time to go through this, but this works. Okay, so let me summarize. Here are the, I think, salient features of this algorithm. It's very general. It works for arbitrary, essentially arbitrary convex constraints and concave rewards. Just we need Lipschitz continuity. And this Fenchel duality, I didn't say things in terms of Fenchel duality, but that's what is underlying it. It seems like the very powerful, or at least the right tool to attack this problem. And for a long time, we were struggling with this random permutation versus i.i.d. They should be the same or very similar, but we didn't really have a good explanation. This captures exactly where this comes. So i.i.d. the expectation is the same throughout. The random permutation, the expectation is changing, and it's just a difference. So if you take the random permutation, in every time step you take the expectation of the remaining, and you see how different it is from the expectation of the whole. You sum it up, and that's exactly the extra term you get for random permutation. So it really captures the difference between the two. And the other nice thing is this modular proof, where we use this online learning as a black box, and we don't really care what algorithm you use for the online learning. Earlier problems were very specific to, and even the other work that I mentioned that was simultaneous or later, they were very specific to the particular algorithm you use to solve the online learning. But here we show that okay, it doesn't matter. All I care about is that it has low regret. And this was actually conjectured even back in 2007 when Mehta et al. Came up with this adverse problem. They said, oh, there should be some relation to this experts algorithm, and people, all the subsequent ones hinted at this connection, but there was no formal connection, and we make the first connection. And the other progress is beyond this. Any other advantages, if the learning problem you can get better regret, then that translates to a better computative difference, as we saw with the smooth functions. And of course, this is only limited to i.i.d. It doesn't, so random permutation, this extra term is already 1 over root t, so you can't help it. Okay, I think there's more to do here. One direction, that could be useful is to go beyond these stochastic models that we have. So we have this i.i.d. random permutation, we have some time changing distributions, but these are mostly stateless. So maybe some kind of Markovian process or something, might be able to extend it. The other problem is, so there's a scheduling version of this which doesn't quite fall in this general framework that I mentioned, and I think figuring out similar algorithms and similar guarantees for the scheduling would be very interesting. So we're working on this with Paolo and others. And for me personally, another thing I would like to see is more applications of this. It seems like a very general framework, so I'm interested in, okay, what are the other problems that people have worked on that we can formulate in this framework. Maybe that will point to some other ways of extending the model. So maybe they won't fit in exactly, but it's close enough that we can extend it. So thanks.
Questions? Can you go the other way? Like, is there a connection? Like, suppose I told you some convex programming.
It's a good question. Maybe.
Just like you just told us it's duality, right? Yes. We should go to it.
Possible. I wouldn't rule it out. I actually haven't thought about that, but it is definitely possible.
There's some recent work on in the worst case analysis of online algorithms with convex costs.
Yeah.
How are these algorithms related? I mean, I know this.
The problems are a little different.
But the resulting algorithms, are they similar? I mean, because
not sure. I think the algorithms are they similar? No, probably not. The problems themselves are different. So there you have to keep covering at every time step. So you have to maintain so that makes a difference, I think.
So you have more freedom intuitively to.
Yeah, we only have to satisfy it at the end. So I can say we have more freedom, and also we're crucially using the stochasticity, or maybe not so crucially as Seb mentioned. Yeah, actually that's a good point.
You can just state it as a condition.
Yeah, but also this only is it holds only in expectation in some sense. So it doesn't follow that condition may be too strong, right?
No, I was saying
it's like two statements, either this or that.
No, you can say this. I mean that you have a distribution that satisfies this. The distribution could be, John product. I mean something.
Yeah. Okay. Yeah. That's a good point.
Even with some factoring, then the theorem would be that the factor goes into it.
So this is what you're saying is actually very similar to this time varying distribution model that I mentioned but didn't say.
Okay.
It's very similar to that. In some sense, that's what this time varying distribution does. Still, each step has to be independent of other steps, but that distribution in some sense has to include this X star.
Are you results tight? So
yeah. So even for the linear version, this 1 over root t is tight.
And for unconstrained as well.
Yeah. Unconstrained. So you can, I guess this linear version you can just think of it as a distance from the set kind of thing. I think, I don't know, Balu. Even for just minimizing a function. Yeah, I don't know. But at least for the packing problem, you have a linear function and you have packing constraints. It's tight. For instance, for smooth functions, it's not. I mean, you can get this log t, right? So, for instance.
Are you now replacing the?
That's a good question. So the thing is, even though it's only a linear version that we solve and the rest is hack, the algorithm works very well. So it works so well, they're so happy with it that they're not developing on the algorithm anymore. So they're focusing on other things. So currently they're happy with the algorithm as it is. So maybe at some point of time they come back to it and want to revamp it. Maybe then we would get them to use this. But as of now, they're quite happy with it. So
right now it's a linear model?
Yeah.
No need to solve an NLP. You're not solving an NLP in production.
So, yeah, they are solving an LP. They solve this LP offline, and then that kind of feeds the online. The online, they don't solve an LP. It's just this. Yeah, the offline LP is big.
What are they using there?
So actually, they're using the same algorithm.
What tools are they using for that?
So they're using the same algorithm. When you have to solve it offline, you can shuffle the order. So you're getting a random order. So in that way you can solve that.
Yeah.
that's what it is.
Well, I think there's another interesting model. So in your of course your bound is performance bound in terms of t goes to infinity. You have this expand. But think about in reality, it's just not really infinite things. But that means your AT is actually is sampled from the finance side. So if you sample from finance side with certain distribution, then when you do this 1 over t something, you are actually going through the same things repeatedly. Can you use some learning? I mean, can you gain something if you go with same request second or third time?
But that's the thing. I don't think the support of this distribution is small. Right? It's a distribution on sets of vectors, and the support of this distribution I don't think is small. I think the support is much bigger than t. In some sense. That's how I would model it, right? Or at least as large as t.
Well, what happens if the support is much smaller?
If the support is small, then yes, you could actually learn the distribution and do something simple. But every impression is essentially different in some sense. So the support is huge, and that's why we need to do something other than learn the distribution.
Thank you.
Thank you.